Good day. For those of you who do not know us, we're the instructional staff for ECE 150. In this topic, we're going to describe the counting sort algorithm. So in this lesson, we will describe a different approach to sorting an array. What we will be doing is we will be counting the number of the different values that are stored in the array. We will consider two different implementations and discuss the merits of each, and we will compare and contrast this counting sort algorithm with the previous sorting algorithms that we have already seen: insertion sort, selection sort, and a brief review of merge sort. Now here's a slightly different sorting problem. Suppose I have a sequence of coins and I'd like you to sort them. Now you're thinking about this and saying, well, wait a second, I could use insertion sort, but that seems a little bit unnecessary. After all, then you'd be swapping around a whole bunch of coins, and a kid in grade 1 can sort these coins. So wouldn't it be easier just to count how many pennies there are, nickels, dimes, quarters, 50-cent pieces, loonies, and then toonies? After all, just looking at these, I see 4 pennies, and there's 2 nickels, 2 dimes, 2 quarters, 5 50-cent pieces, 3 loonies, and 4 toonies. There wasn't much work done there. I just counted how many there were of each coin, and after that I could sort them. Indeed, I could sort them with different coins instead of the originals, and it would still end up being a sorted list of as many coins as there were originally in this sequence. So now we have to ask ourselves, why is it faster to sort a whole bunch of coins than it is to sort the same number of random integers? Well, first of all, the number of possible values is much more limited. We only have 7 different denominations. Also, there's likely to be duplicates. So suppose we had these same conditions with an array of integers. That is, we have an array of integers, but the values in that array are restricted to values between 0 and n-1. How could we create a sorted array given the fact that we have a limited number of integers that we are sorting, and we do not want to use insertion or selection sort? So going back to our coin example, here's probably the wrong way to go about it. Go through the sequence of coins and find out how many pennies there are. Then repeat the process, counting how many nickels there are, etc., etc., etc. for each subsequent denomination. As you can imagine, that's rather expensive. Instead, more reasonable would be to keep a tally of how many pennies, nickels, dimes, etc. there are, and then walk through the sequence of coins, ticking off how many we've seen of each. So here we have our sequence of coins, and starting from left to right, we see that we have a nickel, a toonie, a loonie, a quarter, a penny, a loonie, another penny, another toonie, and so on and so forth, walking through the entire list of coins, checking off how many we see of each. Having gotten to the end, we now know that there are 4 pennies, 2 of each of nickels, dimes, and quarters, 5 50-cent pieces, 3 loonies, 4 toonies, and now we can quite easily create a sorted list. So the algorithm that we are going to implement is quite straightforward and does exactly what we just did with the coins. We will create an accounting array of capacity n, and we will initialize each of the entries of that array to 0. We will then go through the array to be sorted and just increment the corresponding entry in the accounting array. So suppose we are asked to sort this array. And suppose someone told us a priori that none of the values in this array exceed 9. Consequently, we only have to create an array that has indices going from 0 to 9, and therefore its capacity will be 10. All of these values are initialized to 0. We will use this array to count how many 0s, 1s, 2s, etc. all the way up to 9s there are in the original array. So now we go through the original array with a for loop and we count. There's 1 6, so we will increment the value at index 6 of the second array. There's a 1 next, so we will increment the value at index 1 of the second array. Next we come to a 6, so once again we increment the value at index 6. Then we see a 0, so we increment the value at index 0. Then we increment the value at index 5 to 1, increment the value at index 0 to 2, increment the indices or the values at indices 3 and then 4 both to 1, then increment the value at index 3 again to 2, increment the value at index 0 to 3, at index 9 to 1, at index 4 to 2, at index 8 to 1, at index 9 to 2, at index 3 to 3, index 8 gets incremented to 2, index 1 gets incremented to 2, index 2 now gets incremented twice to 2, index 8 gets incremented again to 3, then index 3 gets incremented to 4, index 5 gets incremented to 2, index 6 gets incremented to 3, and finally we increment the value at index 8. Now we're done. Well, almost. There's one interesting point here. We don't even care about the original capacity of the array because the capacity of the original array equals the sum of the values in our second array we created, 24. Okay, let's implement this algorithm up to this point. Here is our function definition. And we, of course, have the first two parameters which we're familiar with. We have the array that we are sorting and its capacity. However, we now require a third parameter, max value. This is the maximum value that can appear in this array of integers. Notice we cannot sort doubles in this case. So here we have an array that we are assuming has values between 0 and max value. They may actually be integers on a different range, but you can implement that algorithm yourself. The first thing we have to do is create an accounting array, and that is going to have to be able to store indices from 0 to max value, and therefore its capacity will be max value plus 1. We will initialize all the entries of that array to 0. Next, we have to go through the original array that we intend to sort, and then what we need to do at every single step is increment the corresponding entry in our accounting array. So we are going to be incrementing the accounting array that we have just created, but which index do we increment? Well, actually, it's just whatever value is at index k of the original array. So if at index 0 of the original array there's a 6, then we will increment counting array's 6th entry. After this, all we have to do is repopulate the original array with the entries we have counted in the correct order. Therefore, given these two arrays, we now have to create a sorted array. Now, to sort an array in selection sort or insertion sort, we had to assign values to temporary values, we had to swap entries, we had to move entries. We're not going to have to do that here. Instead, we're going to proceed as follows. We're going to have a for loop, but that for loop is now going to go through the entries of the second array. Now, the first entry of the second array says that there are 3 zeros, so we will set the first 3 entries of the original array to 0. We don't care that there are more zeros there. The first 3 entries are 0. The next 2 entries will be set to 1. The next 2 entries will be set to 2. The next 4 entries will be set to 3, and so on and so forth, having 2 4s, 2 5s, 3 6s, no 7s, 4 8s, and 2 9s. We suddenly have a sorted array. All right, so now take a minute, pause this video, and try to design an algorithm to repopulate the original array, given now that we've counted how many values there are of each from, say, 0 to 9. So this is what you have to start with, so good luck. All right, hopefully you took some time to try to devise your own algorithm. And so finishing the algorithm, let's go back and take a look at the information we have. So what we want to end up with is an array that has 3 zeros, then 2 1s, 2 2s, and then 4 3s, and so on and so forth. So it seems as if we are going to be having a loop that goes from 0 up until the maximum value in the array. All right, so here is our for loop going from k assigned 0 or initialized with 0, going up until k is, as long as k is less than or equal to the maximum value in our array. Now what we want to do is we want to populate the original array with 3 zeros and then 2 1s. That sounds like another array or for loop. So we're going to have a for loop that will run as often as there are entries in the corresponding array that we see here. So when k is equal to 0, this inner loop will run from 0 to whatever value is stored in counting array at index 0. Specifically, it will run from 0, 1, and 2, so it will run 3 times. Then with the next iteration of the outside loop, k is equal to 1. So the inner loop will run from 0 up until but not including counting array entry 1, which is 2. So that loop will run twice. Each time we are going to have to assign the original array the value that we are currently at. So first 1, then 2, and so on and so forth. So we need some sort of index, and that index will tell us where we are in the original array. So this index into the original array must be initialized outside of our for loops. So position is initially 0, so we're first going to update the first entry of the original array. Once we have done that, then we will increment the position and we will update the next entry, and so on and so forth. And this is just going to go through the original array, and it will copy 3 zeros into the first 3 entries. Then it will copy 2 1s into the next 2 entries, and so on and so forth, each time incrementing the position where we are placing the next entry. And notice that position was declared outside of these two for loops and initialized outside of these two for loops. Hence, the only time position is incremented is when we are assigning one further entry in the original array. We can also make an assertion at the end of this algorithm. We should have that the index position should equal the capacity of the original array, as we've just filled it up. Here is a second approach that we could possibly use. Here is our counting array, and it stores how many of each value from 0 to max value there were in the original array. What we will do now is we will create a second array, that is, one with an additional entry. So this has a capacity of max value plus 2. What we will do is we will define the kth entry of this second array to store the value that is equal to the sum of the entries from index 0 to index k minus 1 in the original accounting array. So, for example, index 5 in this second array will be the sum of the values at indices 0 through 4 of the original array. So that would be 3 plus 2 plus 4 plus 2, which is equal to 13. Similarly, the value at index 7 would be the sum of the entries from index 0 to index 6 in the original counting array, which would be, well, 13 plus 2 plus 3, which is equal to 18. We could do this for each entry, and thus we could populate this second array. Well, let's implement some code to do this. So here we have a cumulative array of capacity max value plus 2. So the entries go from 0 to max value plus 1. Let's initialize all the entries to 0, although that may not be that necessary. We really only have to initialize the first entry. And now we're going to do a loop. That loop will start at index k equals 1. Because the value of the 0th index is going to be 0 anyway, because there's nothing before the 0th index of the original array. So we're going to fill up this array starting at index 1. Now, the hard way of doing this would be to count the number of or sum up the values from index 0 to index k minus 1 in the original array. That's going to be a little bit expensive. So instead, you might note that, oh, wait a second. If the cumulative array has a value of 13 at index 5, then the value at index 6 is 15, which is 13 plus the value at index 5 of the accounting array. 13 plus 2 is 15. Then at index 6, 15 plus 3 is 18, which is the value at index 7. 18 plus 0 is still 18. 18 plus 4 is 22. And finally, 22 plus 2 is equal to 24. So rather than counting up all the previous entries, all we do is we take the previous value in the cumulative array and add the corresponding entry of the accounting array. Well, that's a little bit easier. Also, having finished this loop, let's just check to make sure that that last entry in the cumulative array is equal to the capacity of the original array. So how do we now use this new cumulative array to populate the original array? Well, this new array is essentially saying indices from 0 to 3 minus 1, or indices 0, 1, and 2, should be populated with a value 0. Next, Indices 3 to 5 minus 1, or indices 3 and 4, should be populated with the value 1. Next, indices 5 to 7 minus 1 should be populated with the value 2. Next, indices 7 through 11 minus 1 should be populated with the value 3. And so on and so forth. And noting that the array also says that for the value 7, the value at 7 is 18, the value at 8 is 18. So this says that indices 18 through 17 should be populated with the value 7. Well, that's essentially saying no entries of the array should be populated with the value 7. Carrying on, indices 18 through 21 should be populated with 8, and indices 22 through 23 should be populated with the value 9. And we are done. So let us finish our implementation using this alternative approach. So now we will be going through each possible value, and the entries of the array that should take on each of these values go from the index at cumulative array of value up until but not including the index of the next value in the cumulative array. And then we just assign that kth entry the value that should be at that location. So why are we discussing two approaches? After all, in a sense, the first approach we showed was superior as it didn't require that second intermediate array. We only needed a single counting array where we counted how often each value appeared in the original array. Well, the goal here is to demonstrate that there are nevertheless different algorithms that can solve the same problem. And in reality, you may come across situations where instead of having a counting array of values, you may actually only have the cumulative array, in which case you could just use that directly to fill up the final array. Again, it's just a second approach and therefore a different idea that you can consider if necessary. So the question is, how much faster is counting sort than, say, for example, insertion sort? The answer is, of course, it depends. Suppose that we had an array of capacity 10 and we called insertion sort on it. Well, that should be sorted rather quickly. If, however, we were sorting an array of capacity 10 and the possible values in that array range from 0 to 1,000,000, if we were to call counting array on this, this would require us to allocate memory for an array of capacity 1,000,001, initialize all the entries in that array to 0, and then, well, going through the array and incrementing the values isn't bad. That will be very quick, 10 steps. However, then we have to go through that second array of capacity 1,000,001 and copy the appropriate entries back. That's going to be painfully expensive. So in this case, insertion sort is likely the ideal sorting algorithm. On the other hand, if you tried to call insertion sort on an array of capacity 1,000,000, you would find it would actually take on the order of about a day to sort that array. That's a lot of time. If, on the other hand, you were to sort that array using counting sort, and let us assume there are 10 or maybe even 100 possible values in that array, then this would actually sort in under a second. Now, insertion sort may actually also sort in under a second, but that's only if the array is either completely sorted already or almost completely sorted. Now, how do we define almost completely sorted, and how do we determine the runtime of these algorithms? Well, you will see that next in your course on algorithms and data structures, where you will learn about asymptotic and algorithm analysis. Indeed, in your calculus course, you may have already seen big O notation. That is the notation you will be using in your course where you do algorithm analysis. Now, what's significantly different between this counting sort algorithm and the other sorting algorithms we've seen? Up until this point, you've definitely been exposed to insertion sort and selection sort. You may also recall our discussion on merge sort. So what is the fundamental difference between these sorting algorithms and the one we are looking at in this topic? Well, in the first three, the entire algorithm was based on comparing the existing values in the array. So, for example, here in the insertion sort helper function insert, we compare one entry of the array with a different entry in the array. Consequently, all three of these algorithms that we saw initially depend on being able to compare various values within the array, and we sort them based on their relative locations. This counting sort algorithm never compares entries to each other. That is the fundamental difference, which is why it can, under certain circumstances, be exceptionally fast. So, following this topic, you now understand the idea behind a counting sort. You have seen two different implementations. The first puts the appropriate number of each value into the array. The second uses a cumulative array to determine what goes where. You understand that there are circumstances where this algorithm will be faster than insertion sort, for example, and other circumstances where it will be slower. You are aware that what fundamentally differentiates this algorithm from the others we have seen is that it does not compare the relative values of entries of the array. We simply count the values of what is in the array. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!